50 hours of work, 24,576 pixels, one computer screen. The resolution of the screen is twice as much as the resolution of the TI-84 graphical calculator. It can display 16 lines with 32 characters each, 512 characters in total. So I call this screen SBX 512. Another nice feature of this screen is that it supports custom characters, so you can write anything you want and show it on the computer screen. Fun fact, I made the screen 3 years ago because I really wanted to finish the electricity tutorials first. Also, it takes 2 minutes for the game to load the screen. In the future I want to add a user interface with multiple programs, of which a text editor with maybe multiple text files. And I want to add scrolling. I want to add a settings program where you can edit your characters using this interface. And also I've got to wire up display B because there's nothing here yet. This computer screen is actually 2 screens. It's this 16 by 16 screen and another 16 by 16 screen. This would allow you to do some multitasking or maybe multiplayer games, or perhaps menus with a list on this screen and a preview of the selected item on the other screen. I also made a new keyboard with many optimizations compared to my previous keyboard. I've also improved the large keys like the shift key and the control key. And we have sound. We have a memory bank data input hall, so you can copy things like music data to import them into this computer screen, in a future version of course. And we have these game controllers. So there are 2 game controllers. There's this one for cursor games. Over here you can see what it's reading. So this is forward, backwards, left, right. As you can see, there's a bit of latency, but that's no problem because it's a cursor game. And we have some buttons. And here's the next game controller for low latency games like Tetris, because I really wanted to make Tetris on the screen. Which I'm of course not going to do anymore. But I will make a graphics processor which can run Tetris. And we have some more buttons. These buttons work better on mobile, by the way. And we also have this. Isn't it? How does it work? How do I power this? Okay, I didn't wire that up just yet, but now I'm inside a button, so wherever I look, I'll press that one button. Which could be useful for some games that use less buttons. And also we have sound for the games, which don't do anything at the moment. But here's a start for a sound card. The border displays that are used to show the cursors have many more patterns programmed inside of them. Fun fact, when you load a Survivalcraft 2.1 version of the screen, the game will convert it to Survivalcraft 2.2. But due to the massive load of loading the screen, the texture mapping gets glitched. How does it work? It all started with an idea. An idea to make this unit, which was a concept for a better computer screen. I left the idea render out overnight, and when I woke up, I could make this. This is what makes this computer screen work. I copied 512 of these to make that computer screen. You can see them in the back. I copied them over using World Edit. And then the outputs from these units are combined horizontally and then vertically into one display. And here's one of the horizontal combiners. So all the outputs from all the units come in here. And then they're all combined. The signal flows like this, and it takes this corner, and then it takes this corner to form one output, one screen. How does this work? The outputs of this unit are the pixels you see on the screen. These pixels come directly from memory banks. For each one of these 12 4LEDs, there's one memory bank. And this was just a testing pattern. The resolution is actually twice as high as you see here. This unit can hold an image. This is the image which it's currently holding. To write a new image in it, we need to supply an image with all these wires into all these memory banks. Then we need to send a signal to write it, and then these memory banks will output that image to the screen. So as you can see, these memory banks are sandwiched between these lines of data inputs and data outputs. But there are more connections. These are the clock inputs of a memory bank. They're all collected to this wire. This is one of the two data location inputs of a memory bank, and they are collected in this wire. And here's the other data location input of a memory bank. And all of those are collected in this wire. The hardest part in designing this unit is to make it as small and compact as possible. Because the bigger it would be, the more space it would take. And the bigger the screen would be. I built this with the 128 build height limit. So that would mean that I would have to make a smaller computer screen. So I wanted to make it as compact as possible. So for each character, each image, it takes 2 extra blocks of height. And this face doesn't interfere with this face. And it takes only 1 block of extra space horizontally. Because this wire can stay nicely on this side, while this wire stays nicely on this side. And that's the reason why this wire and this wire are both red. Because they can just stay where they are without interfering. These wires can just stay where they are without interfering. And in this section here, all these control wires are connected to this neater layout of wires. And in this part, all of the 12 wires that make up an image are connected to these 12 wires. And the neat thing about this linear layout is that it connects right through it. So when image data comes in here, it will come out here, which is connected to the next unit, which comes in here and goes out here. Here you can see it in action. So the data comes in here, and then it will go in this unit, and it comes out here, where it's connected to the next unit, which will take the data, and it comes out here to the next unit, and the next unit, and the next unit, and the next unit. So in other words, when data is specified here, it will be sent to all units in this row. And this data is also connected to the next row, and the next row, and the next row, and the next row. In other words, when data is specified here, it will be sent to all units. And then in this last section here, all the control wires are wired up. So these are the location inputs for the memory banks, which I'll use for scrolling. I haven't used them yet, but I'll be using them. And here's the wiring. It's just connected to its neighbors, just like these. And finally, the clock input, which is necessary to write data into these memory banks and to read it. And we will only write data to these memory banks if this unit is the selected unit. Because it doesn't matter if there's data in these data inputs, as long as it doesn't receive a signal to write. That's why I decided to share this data input with all units. But this clock input for the read and write signals are only going to be sent to one specific unit. The unit where the cursor is. And to select a unit, I use this. It's what I call an AND grid. What it does is there's a vertical wire and a horizontal wire, and the two are connected in an AND gate at this intersection. So from the side we have an input for each line, and if we turn on two lines, only the unit which is at the intersection of those two wires will activate. And one of these lines will also send the read and the write signals for the memory banks. I chose to use the bottom one. And there's also this wire, which is totally unnecessary, but I didn't know that at the time when I made this. So basically what this wire does is it selects this unit and all the other units in this column. Here is the back of the display, which has many of these AND gates, which form a massive AND grid. So this is one of those horizontal wires. Here's another one. And this is one of the vertical wires. And here's another one. So if I select this horizontal wire, and I select this vertical wire, then at this intersection it's gonna turn on. While at the other intersections it won't turn on. This is because this wire is not activated, even though this wire is. Only one of the two inputs is activated, so this AND gate will not activate. Same goes for this one. This input is activated, but this one isn't. So this AND gate will not activate. And here both aren't activated, so this AND gate also won't activate. But this AND gate has this input activated and this input activated, so this one will activate. So this unit is selected. And this technique allows me to manage all these units just from the sides, which removed a lot of complexity. Because instead of managing all 512 units, I only have to manage the sides, which is only 16 by 32, which is 48. But besides just activating the unit, I can also send some signals to it. So in this computer screen, I'm sending read-write signals to it. So F, the maximum signal, will trigger all memory banks to read, while a low signal like 1 will trigger the memory banks to write. So let's send a write signal. Let's see, where can I fit a battery? So now this battery is connected to this wire. So if I change the voltage in this battery, the voltage in this wire will change, and also the output of this AND gate. Because AND gates in Survivalcraft use bitwise AND for these 4-bit values. And a nice thing about it, if one stays at the maximum, the other one will pass through unchanged. So if I set this to 1.3, it will output a D. And 8. I don't actually want to send a write signal to this unit, because that will... you know what, let's do it. Oh, there's no data in anyway, so we'll just do it. So let's send a write signal to this unit. I always just pick one, but you could use any other low signal. 1. And let's write it again. Now the input data is written into this unit and sent to the output. And this unit also received a read signal, which will make sure that the unit will also output this data. Since there was no data, there's not much to see on the screen, besides a backspace if there was something in there already. To send these signals from the sides, I'm using these memory banks. And all these memory banks are connected to 2 wires. And these wires have values in them. This wire sends the read and write signals, while this wire sends the x-coordinate of the cursor location. And these memory banks will check if the value of the x-coordinate input matches with their position. And also the horizontal wires are connected to these memory banks, which do the same as these memory banks. But the difference is that these memory banks don't have to send read-write signals, so they will only react to this wire, which is the y-coordinate. Let's just remove this temporary setup, reconnect it, and do the same for this one. There are already coordinates coming in, so let's just isolate this. And now let's add my own coordinates. And we'll go to coordinate 1, 1. And I'll set it to read. And now as you can see, this wire has turned on. And this wire has turned on. Because the y-coordinate value is 1. And this memory bank looks at this input value. And when the input value is 1, it will output the maximum signal, F, which is sent to this wire. And the same happens here. So the x-coordinate value is 1. So when the x-coordinate value is 1, this column is activated, which is this wire. And I defined a few operations. So 0, it's idle, it will output nothing. 1, it will send a write signal to the selected unit. 2, it will send a read signal to the selected unit. 3, it will write all units that have this x-coordinate, which is the entire column. And 4, it will read all units that have this x-coordinate and are in that column. And 5, it will write all memory banks in this computer screen, which is useful if you want to set the entire screen to the color white, or you want to clear the entire screen. And 6 will read all units in this computer screen. I've currently set it to read, which is code 2, so let's now set it to write, code 1. And now as you can see, this selected unit now receives 1, which is a write signal. So this unit will be written with this data, which is empty. Half of these memory banks are used to select an entire column, which, as mentioned earlier, is unnecessary. Either way, this memory bank is used to set the first column to on. So the x-coordinate is 0. It will send a write signal at code 3, which is write this column. It will send a read signal at code 4, which is read this column. It will send a write signal at code 5, which will write all units. And it will send a read signal at 6, which will read all units. And here's a concept for the character location inputs, which I have done not that much with. Now let's just chop these wires and connect this again. Remove this place. Clean these wires. Almost there. You want to go? That it? Okay, so. Hit the buttons. And I guess that's it. So, to control this display, we have this ribbon cable of data inputs, define a character, an image. And we have these control inputs. One that specifies the operation. One that sets the x-coordinate for the cursor. And one that sets the y-coordinate for the cursor. This ribbon cable for the character data is connected to many devices, which makes it a bus. And there's also this device, which has a memory bank connected to each one of these wires. So the outputs of these memory banks are connected to this bus, and also the inputs of these memory banks are also connected to the same bus. And there are big switches to turn a connection on or off. And there's this, a nice drawing board, which is now encoded. Or is it? Is it on? Now it's on. Which is now encoded into this data bus, so that I can send this character data to the computer screen. I also made this display, so you can see what's going on in the bus. And the coordinates and the operation you can see up here. As you can see, now the smiley comes in here. Now it's sent to all units. Every single one of them will get the data for this smiley. Let's now just select this unit down here and write the smiley in there. For this unit has coordinate 0, 0. And we'll write and read. Now let's see our smiley on the computer screen. There it is. Our little smiley in the corner of the screen. This unit is used as a memory for predefined characters. So a character which I can draw in here can be sent to the data inputs for all these memory banks. And when I send a signal to write these memory banks, that character will be written inside these memory banks. Each memory bank will store 4 pixels inside one of these slots. And there are 256 of them, so with this unit I can store 256 predefined characters. These characters I can also load into the same bus. And of course the characters stored in here are ASCII characters. So the alphabet with capitalized letters and non-capitalized letters, the numbers and some basic symbols. And this setup here is the only bit that's really messy. So I've used this to write all the ASCII characters, and this here is used to control the cursors. The enter key, the backspace, the arrow keys, all the things that will change the cursor location. This screen has the same character size as a TI-84 graphical calculator. I believe it also has the same font, which means that I could use some of its math symbols for this screen. Also, the TI-84 can show 8 by 16 characters, while this screen can show 16 by 32, which is exactly twice as much. I've been writing retro games and tools in low-res NX for more than a year now. What's funny is that the screen has a very similar resolution to the low-res NX Fantasy console, which has a resolution of 128 by 160 pixels, while my screen has a resolution of 128 by 192 pixels. Both are character-based, which means that you can only write a group of pixels at a time, which is limiting compared to screens that can load single pixels. But for text, and also for tools, and for most 2D games, character-based displays are just fine. This screen of mine doesn't support sprites, and it can only write one character at a time, which means that if I do end up making games like Mario for this screen, there won't be too many moving enemies. But I can make games like Minesweeper and chess just fine. Now I think that's enough about the display. Let's go to the keyboard. Thank you so much for watching this video. God bless. Making educational videos is so much harder than making gaming videos. That's one of the reasons why I don't upload that often.